The plan for today is we're going to go ahead and continue the subject of ecology, specifically talking about seasons and biomes and airflow patterns. But first, we're going to revisit the topic of latitude. As mentioned last time, I do expect you all to know what our latitude is, at least to the nearest degree, which is 34 degrees north. And in office hours, I was chatting with some students about, do you know how to find latitude on your phone? And I was actually surprised that most of the students there actually didn't. So I thought, well, let's have a quick demo here. Here's my phone. Let's see, make sure there's nothing, no incoming messages. Nope. All right, we're good. Here's my phone. Okay, let's go ahead and find the compass. Okay, and it'll, of course, depending on what your phone is. Here we go. Here's my compass right here. And so you can notice a couple of different things. One is that there's a large number on top. That is not longitude or latitude. That is the compass direction. So if I point my phone in different directions, it's telling me am I pointing more towards the north or south and so on. Very convenient. So you really should know about this on your phone. But below that, in much smaller numbers and letters, is the actual latitude and longitude. And you can tell which is which because, of course, one will either say north or south, but we're in the northern hemisphere, so it'll say north, and longitude will, of course, say west or east, as it says here. Now notice it says 33 degrees and then 38/44//north. That's our latitude. So what are those slashes and the slashes? Let's see here. Get this back up. So write down what that looked like. It looked like this, all right? So what is this? North. These are the degrees, and then degrees are further subdivided into units called minutes, strangely enough. So what this is a 60th of a degree. That's why it's called minutes, in analogy to a minute being a 60th of an hour. And then similarly, these are referred to as seconds, which is a 60th of a minute. So that's how you figure out what these things mean. So obviously, because we've got more than 30 minutes of the degree, we're more than 33 and a half degrees. So 34 degrees is nearest. Is our latitude to the nearest degree. So as you'll see as we talk about the importance of latitude on local climate, then we can put this in the context of our own latitude. So let's consider now seasons or changes in the temperature and other weather-related issues as a function of the annual cycle. And I'm curious if you know what actually causes the seasons. So I'm going to go ahead and do this as a clicker question with any response counting. So what causes the seasons, meaning, for example, winter versus summer? I've given you 3 different choices here. You can pick your favorite or confer with a neighbor. A, changing distance of the Earth from the sun caused by the elliptical orbit. B, the tilt of the Earth's axis. C, the variability of energy output by the sun. I don't know, what do you think? Chat with your neighbors, click in what you think is the best answer, and we will discuss this. Okay, latecomers coming in might want to quickly consider what causes the seasons. Everybody else should be clicked in. Right? Alrighty, I'm going to shut this down. Let's see. Many of you got this right. Fantastic. Yay. Over 3/4 of you. Excellent. Absolutely. It's the tilt of the Earth's axis. This is really important in causing the seasons, or is the fundamental reason why, in fact, we do have seasons. And so this is actually an extremely common misconception. And so I thought I'd play a 1-minute clip for you that is from an interesting documentary called Private Universe, which is about common misconceptions in the sciences. And this documentary was made by videographers going to a Harvard graduation and interviewing the graduates about some common misconceptions, including what causes the seasons. Let's go ahead and start this up. I'll adjust the volume if it's too loud here.
Many of these students will graduate from college with the same scientific misconceptions that they had on entering grade school. To test how a lifetime of education affects our understanding of science, we asked these recent graduates some simple questions in astronomy. Consider, for example, that the causes of the seasons is a topic taught in every standard curriculum.
Okay, I think the seasons happen because as the Earth travels around the sun, it gets nearer to the sun, which produces warmer weather, and gets farther away, which produces colder weather, and hence the seasons.
How hot it is or how cold it is at any given time of the year has to do with the closeness of the Earth to the sun during the seasonal periods.
The Earth goes around the sun, and it gets hotter when we get closer to the sun, and it gets colder when we get farther away from the sun.
These graduates, like many of us, think of the Earth's orbit as a highly exaggerated ellipse. Even though the Earth's orbit is very nearly circular, with distance producing virtually no effect on the seasons, we carry with us the strong, incorrect belief that change in distance is responsible for the seasons.
Right, so that's a very interesting documentary. If you ever get a chance to watch the rest of it, I really encourage you to do so. It's very interesting. I mean, here we have some smart, articulate individuals who don't quite understand the fundamental cause of what causes seasons on our planet. So this is a figure from your book that's similar, or a figure that's similar to what in your book. It's not actually the figure from your book because it includes a little bit of additional information that is missing from the figure in your textbook. So I'm using this as a visual backdrop to discuss the issue. So we're going to go into this in a bit more detail here. So why exactly does the tilt cause the seasons? The tilt of the Earth is 23.5 degrees, and that is the tilt of the axis around which the Earth is spinning as it makes its circular or slightly elliptical orbit around the sun. And of course it takes a full year to go all the way around the sun, and during this year the tilt does not change. It stays at 23.5 degrees centigrade. But because of this tilt, there are some points of time, such as if we start on the left here in June, where the tilt is such that the northern hemisphere of the Earth is pointing towards the sun. What is meant by the northern hemisphere? We can consider the hemisphere as dividing the spherical Earth into two at the equator, right? So the northern hemisphere just meaning a half, right? And then this is the southern hemisphere, right? Hemisphere. So the northern part of the planet is tipped towards the sun during June, and then in the opposite end of the year, in December, it is the southern hemisphere that is actually tipped towards the sun. And so this makes a difference then in terms of exactly which part of the Earth's surface is getting the direct sunlight, that the sunlight is hitting this the Earth sort of square on here. And so you can see at the equinoxes, which are the midway point temporally between the two solstices, June and December, at the two equinoxes is the time where the sun is directly hitting the equator, as shown in this particular diagram. And in June, in fact, the sun is directly hitting the Earth bang on at a line which is where? This is the line of 23.5 degrees north latitude. And then in December, this line here, not surprisingly, is 23.5 degrees south latitude. So, so the sun is directly overhead at different parts of the planet at different points during the annual cycle, but there are some parts of the planet in which the sun is never directly overhead. Now, why do we care what the angle is of the sun striking the surface and whether it's overhead or not? It's because the warming of the surface will be directly related to the angle with which the sunlight is striking the local part of the surface. So this is somewhat similar to figure 52.6 from your textbook, but has some additional information, so I'm using it instead. So for example, if we consider the equinoxes, when the sun is in fact hitting the earth straight on at the specific location of 0 latitude, so the equator, then it should make intuitive sense to you that the same amount of sunlight is striking a smaller area at the equator than if you compare a comparable amount of incoming sunlight at a higher or lower latitude, in which case the sun, the same amount of light is being spread over a larger area, so it's less intense. And in addition, is passing through the atmosphere at an angle, so more of the incoming light is in fact absorbed by the atmosphere as well. So the sun is much more intense where the sun is directly overhead. And so this is significant both in terms of heating and also for light available for photosynthetic activity for the producers. The lines of 23.5 degrees north and 23.5 degrees south have special names. They're the Tropic of Cancer and Tropic of Capricorn. And so these then are the lines where the sun will be directly overhead at one solstice or another. Now, I think it's a little difficult to wrap your mind around this, so I thought, well, I'll do a little demo on my document camera. Okay, let me zoom out. So this is exactly the same figure that we were just looking at on the screen, but this is now a piece of paper, and I've cut out the Earth so that I can show you that as one leaves the equinox, then the incoming sunlight will be at a different angle relative to the Earth, so we can visualize that by just simply rotating the Earth. And so I'm doing that until I line up the 23.5 degrees south with where the sun is directly overhead, right? So at this point then it would be the middle of the summer in the southern hemisphere, and then if we tilt back the other way, then this would lining up the 23.5 degrees north with sun being directly overhead. This would be the middle of the summer then in the northern hemisphere. Okay, so it's never beyond, it's never more extreme than that, nor is it never more extreme in the other direction. Okay, so you can play around with cutouts like this if this will help your intuition of understanding how the sun is striking the Earth at different angles, at different times. Okay, so this then translates into the sun taking a different path through the sky for any given location in the different seasons. And so I've got a diagram down here in the lower left. So let's go ahead and examine this as a clicker question. If you understand the movements of the Earth around the sun and how the tilt affects the apparent position of the sun in the sky, then hopefully this will make sense to you. So here's the problem I'd like you to consider for this clicker question. A person sees the apparent movement of the sun in the sky shown below, meaning this figure in the lower right-hand side. And so here's the figure we were looking at before, which is slightly obscured, but just to remind you of what we were talking about. I say apparent movement just because, of course, if we think of the Earth as moving around the sun is not rotating around the Earth. But from the point of view of a fixed position on the Earth, then we're watching the apparent movement of the sun. That's all that means. At this particular location, the sun is never directly overhead, let's assume. So in June, if a person standing there facing south, in June, the person facing south would see the sun rise in the east and go up through the sky and then set in the west. In October, from the exact same location, facing in the same direction south, the person would see, again, the sun rising in the east. It wouldn't go quite as high in the sky if this is October. Again, setting in the west. And then in January, rise in the east, even lower in the sky at its maximum during the middle of the day, and then set in the west. So where is this person if this is what the pattern looks like? Is this person in the northern hemisphere or southern hemisphere? Okay, you got 50% chance right to guess this right. Why don't you consider which one of these you would guess? If you're not quite sure, chat with your neighbor. I'll give you 15, 20 seconds or so to consider this, and I'll check back in with you. Okay, everybody figured it out? So for 99%, that's what I'm hoping for here. All right. Okay, it looks like everybody's clicked in. Let's see what you guys think. Well, 2/3 of you got this right. Well, that's something. Okay, I was hoping it would be a much higher fraction because, after all, this should be quite familiar to all of you because we're in the northern hemisphere, and so I would hope that you had actually noticed that during this summer, the excursion of the sun in the sky, in fact, hit a higher maximum than during the winters. As, perhaps 1/3 of you have not noticed this. Pay attention, see where the shadows are, and get the, see where the sun comes in the windows and so on. It's be useful for you to recognize such things. Okay, let's try one that's slightly more challenging. Okay, we're considering the same pattern. I've actually changed the dates here. So now January looks like this. So the top one is January, the middle one is October, the bottom one here is June. The cardinal directions are still the same. The sun is still rising in the east and setting in the west, okay? We're facing south. This is what we see. And for this specific location, the sun is never directly overhead, okay? So I want to know, can you figure out where this person is? And I'm giving you 4 choices here. Perhaps the person is somewhere between the equator and 23.5 degrees north latitude. Maybe the person is between 23.5 degrees north latitude and the North Pole. Perhaps the person is between the equator and 23.5 degrees south latitude. Or perhaps the person is standing between 23.5 degrees south and the South Pole. Where on the planet is this person if they see this kind of pattern in the sky? Okay, you might want to chat with your neighbors. I'll give you 20 seconds or so and then check back in with you. Okay, everybody figured it out? Okay, this is just a single position, different points in the annual cycle. Where is this person? Okay, I'll see how many of you were able to figure this out. Well, 1/3 of you got it right. Good job. How could you figure that out? Well, at least 2/3 of you got the hemisphere right, which is the same pattern as we saw before, right? Well, okay. Okay, right. So first of all, we can figure out we're in the southern hemisphere, right? Because, after all, the sun being higher in the sky is an indication of what? Summer. If you're in the southern hemisphere, you're having summer when we're having winter up here in the northern hemisphere, right? So the sun is higher in December, January, February in the southern hemisphere than it is other times during the year. So as soon as you look at that, you know that you're in the southern hemisphere. Now, given that the sun is never directly overhead, you immediately know you're not between plus, and you're not between 23.5 degrees north and 23.5 degrees south, because that's the only part of the planet that gets has the sun overhead at any point during the cycle whatsoever. Okay, we're far enough north that the sun is never exactly directly overhead here, so that makes it then D the right answer. This person is too far south to ever have the sun directly overhead. We know that because we're outside the tropics. So, okay, so now that we've got our sun angles mastered, let's go on to global air circulation. And this is similar to figure 52.5 in your textbook, but it has a little bit of additional information that I wanted to cover, so I'm using this figure instead as a visual backdrop. So, the air flowing close to the Earth's surface has certain predictable patterns. These are global averages. Certainly extreme weather can cause permutations temporarily from these overall patterns, but these are the major patterns that one sees in the air close to the Earth's surface. So what are these patterns anyway? There are large circulating cells of air that move perpendicular to the Earth's surface. So you can see them most easily in side view, which is why this diagram is drawn as it is. So let's go ahead and start in the equator. Here's the equator right here. You can't see that, I'm sorry. Let me get a different color. So here we are at the equator, 0 latitude. The equator and the tropics in general, so the tropics would be plus or minus 23.5, right? So here we are in the tropics, is getting the most direct sunlight. It's being heated the most intensively, and the equator is right in the middle of that. The equator is, overall, as an annual average, is getting the most intense sun during the year. So what does that mean? It's hot. Okay, so as the equatorial area is being heated up, then what happens? Well, the air that is being heated, and here we are at the equator right here in a little part that is magnified so you can see better detail what's going on here. The air will then be rising because it's hot, and so as air is heated, then it expands and the density decreases. So we've got rising air at the latitude of the equator, and as it rises, it cools. As it cools, some of the water vapor in the air will condense out, and this then will cause rain. So as the air is rising, we've got rain falling at the equator, and so that makes it very wet in the area of the equator, because this is happening, it's being shown at the side, but of course you should think about this happening in the equator as a whole. So you've got hot, moist air rising at the all the way around at 0 degrees latitude. It's rising all over the entire planet. It's cooling, it's raining, and now we have air with much less water vapor in it, and it has a circulation pattern that was described by a number of different individuals who have been immortalized in the names given to these circulating patterns. So these things, these big rotating gyres are called cells, and these cells have specific positions on the Earth. Let's go ahead and draw this in here. So here we are at 0 degrees, and then up at the top here at the North Pole we're at 90 degrees, and it just so happens that there are 3 cells that form, and so they are positioned between 0 and 30 degrees, 30 and 60 degrees, and 60 and 90 degrees. That's heading both in the north direction and in the south. So here we go. Here's 30 degrees south, 60 degrees south, and 90 degrees south at the South Pole. So we have these huge gyres forming, and we can tell in what direction the circulation is because we're moving in this direction here. I should perhaps erase my rain because then we have a little arrow going in the wrong direction. There we are. Okay? So because the air is rising in this direction, that causes the gyres immediately adjacent to the equator then to be moving in that direction. Okay, so you can figure out which way it's flowing. So, why does that then lead to a pattern shown here where the arrows are not just pointing straight down, as you would think from examining this cell here in more detail. And by the way, this cell here is referred to as the so-called Hadley cell, this one between 0 and 30 degrees north or 0 and 30 degrees south. These big circulating air patterns are called Hadley cells. So notice that farther up away from the Earth's surface, the air is heading in a northerly direction, but closer to the Earth's surface, it's heading more in a southerly direction. What we're looking at here on these arrows shown in this part of the diagram are the direction of air that is particularly close to the Earth's surface, which is the bottom part of this gyre, which is heading in a southerly direction. So if it's heading to the south, why does it also have a bit of a western tilt? It's because the Earth is rotating as the air is also rotating in a different direction. Okay, so this is kind of hard to wrap your mind around. So again, I have a demo for you. Let's try this out. There we go. Here's the diagram that we were just looking at in a projected form. Okay, so this is a flat surface, and we're talking about a 3D thing, so which makes it a little bit harder, but we're talking about air that's leaving the equator, coming up, circulating back down, coming down at 30 degrees, and going around and around in this direction. Okay, so I made a little gyre out of paper for you, right? So here we go. Here's the gyre. So this should make you think of one of these. So in side view, it would look like this, right? And I've got arrows showing the direction of the airflow on here. And of course, if it's going completely around, then the arrows have to be pointing in the same direction all the way around, right? We don't have it going this way and then backing up and reversing, right? We have just constant circulation in this direction, around and around and around. Okay? So if we line this little loop up, then with this one, it would be like that. Right? But looking at it in side view is a little harder to tell what's going on, so let's go ahead and put this gyre in this location right here. So it's between 0 and 30 degrees. Does that make sense? It's coming up at the equator, up and down at 30, and then back around, round and around and around like this. Okay? Now, meanwhile, the Earth is rotating, right? And the sun rises in the east and sets in the west, so that means that the Earth is rotating in this direction, right? And because this is a flat piece of paper, it's a little hard to make it rotate. If I could make it rotate, it would go like this if it was round. But it's a flat piece of paper, so I'm going to have to fake it and just move the surface. So it would move in this direction, right? Or I could just move the air in that direction. But the Earth is actually rotating below the air, so it's a little easier, I think, to understand it if I just move the Earth. Okay, but because the Earth is a sphere and not like a cylinder, then the circumference of the Earth at this point is actually larger than it is farther away from the equator, right? So if we look at the circumference at 30 degrees north, it's a smaller distance than it is at the equator, where it's at its maximal circumference. So as the Earth is rotating, the actual distance traversed is longer as a point moves from left to right in the orientation that you have here, from west to east, than it would farther north. Okay, so a way of sort of faking the motion then would be to go like this, right? Because this bit is moving more and this bit is moving less. Okay, so it would be like this. Okay, so notice that now my little loop here is lining up with the arrows. Okay, so that's just driven by the underlying movement of the rotation of the Earth. Now you might notice that the arrows here are pointing in the opposite direction from the arrows on the top of the loop, and that's because you're looking at the top of the loop here, and these arrows are corresponding to the winds that are closer to the Earth's surface. So if we have a little peak at the bottom of the loop here, you can see it's exactly in the same direction as these other arrows. Okay, so that's what's driving this particular pattern, and the significance of this is that, can I get my computer back? Yes. So the significance of this then is that we have characteristic directions of weather as well, and of the winds. And this is latitude dependent. So the primary, let me erase what I put on here for a second here, so I can show that a little bit more easily. So the prevailing winds then at the equator are in this direction, right? And then farther away, at about 30 or so, the prevailing winds are from the west. So they're referred to as the westerlies. Okay, so you're probably familiar with that. After all, what's our latitude? 34 degrees north, right? And so what's the significance of being around 30 degrees? Well, that's where the dry air, the edge of the Hadley cell is coming down, bringing dry air. The parts of the planet that are associated with 30 degrees north and 30 degrees south are particularly dry globally. Here we are in a fairly dry environment, but also the prevailing winds in our area are from the west, and you perhaps have noticed this. We get most of our weather direction from the west, from the ocean. Certainly there are temporary changes in local weather patterns. Sometimes we get Santa Ana's coming in from the east, but the overall prevailing winds are in fact from the west. And these wind patterns, which head in this direction at the equator and the opposite direction at about 30 and north or south, then also help drive and affect the ocean currents. And so one also gets huge gyres or circulating patterns in the world's oceans, as shown here in the diagram in front of you right now. And so, again, to match up a gyre with a prevailing direction of wind, note that at the equator, if the prevailing direction is like this, then the close part of the gyre has to be going in the same direction. You get a lot of turbulent mixing here. So the gyre is going towards the west at the bottom here and towards the west at the northern end here. So that allows you to figure out what direction the gyres are going in. So we've got a clockwise up here and counterclockwise there relative to your observing angle. So this affects weather then because the water that is in the tropics is warmer. It's being heated directly by the sun, and then it's either moving up the west coast, as it's showing here, or on our in North America, we've got cold water coming down our coast because that's the direction of the prevailing ocean currents. And this is cooler because it's not coming from the equator. So this has a tremendous effect then on the local climates. One other thing I want to point out before I leave this particular diagram is one notable part of the of these gyres that affects the weather. Actually, I think that's the point. Yeah, here we go. So this affects climate by heating or cooling. And so an example is the Gulf Stream, which heads north up the east coast of the United States, and it is very warm water because it's starting in the tropics and then heading north and circulating around the North Atlantic as shown, but part of it peels off and heads off in the direction of Europe. And this is very important in terms of European climate because this has a warming effect on Europe. Europe is much warmer than it would be just simply based on latitude, and that's because of the warming effects of the Gulf Stream. So why is it that water in particular has such a strong effect on climate? And in chemistry, you may have learned about a property of matter called specific heat, which is how much energy does it take to change the temperature of a specific amount of that substance. And water has a very high specific heat, meaning it actually takes a lot of energy to heat up, which means that as it's cooling down, it can also release a lot of energy. And so this then means it has a very strong effect on climate because hot water holds a very large amount of heat. And so the proximity of water, whether it's oceans or large lakes, then tends to have a very moderating effect on the climate of the nearby land. And again, this is something that we experience directly. We're right next to the ocean, which has a moderating effect on our mild climate. So in addition to latitude and sunlight intensity and proximity of water, something else that affects local climate is the topography, specifically mountains. And mountains have an effect on climate because of the effects that mountains have on air as it moves over the surface of the Earth. And this is shown in figure 52-8 from your textbook, which is in front of you right now. In this diagram, it shows airflow approaching the mountain range from the left, from your particular vantage point, and as it approaches the mountain range, it rises just simply because the mountain is in the way. That's what forces it to go up as it follows the local contours. As air rises, it cools. We already discussed that in the context of why does it rain at the equator. So as the air rises, it cools, and this tends then to cause condensation and precipitation, rain, and this is on the side of the mountain range that is called the windward side, is the side that is on the same side from which the air is approaching. Then the air moves over the mountain range, and when it reaches the other side, well, it already lost a lot of what had been water vapor. It condensed out and rained on the windward side. So by the time the air reaches the other side of the mountain, it's extremely dry. And this is one of the reasons that different sides of mountains, specifically relative to the direction of prevailing winds, have these names, leeward and windward. So windward is always particularly wet, and leeward tends to be extremely dry. This is another pattern we see. The very dry areas are on the leeward side of mountains, and windward is on the upstream end of where the air is coming from in the mountains. It's very wet on that side. Students sometimes think that this is necessarily west and east. That is absolutely not the case. It depends on your latitude, right? So this may make you think of California. Actually, we have our prevailing winds from the west, and we have an ocean, and we have mountains, and so certainly we see this kind of pattern here at our latitude of what? 34 degrees north, okay? But if we were at the equator, our prevailing winds would be from what? The east, and we would expect that this same pattern would be in reverse, where the windward side then would be on the eastern sides of the mountains in the tropics. That's where it would be wet, and it would be dry on the western sides, not the eastern sides, if we were at in the tropics. So since we're talking about climate, I think it is important to point out that climate is changing all the time, and the way that one describes climate or the numbers that one pulls out of historical climate data depend on the time scale over which you're evaluating the climate. What I have in front of you right now is not from your textbook. It's actually a figure from Wikipedia, and it shows Phanerozoic climate change. And of course, the Phanerozoic is something that you should be familiar with. This is the last 500 million years or so, right? With the first period being the Cambrian, way down here on the leftmost side of this particular diagram. Time is going from left to right, so this is where we are now, because this is millions of years ago. So we're talking about a huge period of time here. Remember, during the Phanerozoic, we were talking about the 5 different major mass extinctions and so on. And there are some times when it's hot, sometimes when it's cold. The y-axis here is actually labeled as an isotope ratio. That's because that's what can be used to estimate temperature. It's higher, lower. The way to read this is the hotter temperatures tend to be higher and colder tend to be lower, and a couple of glacial periods are shown down here as well. If we take just part of this axis, then again, your impression of how climate changes is greatly influenced by the temporal scale at which you're examining the data. So rather than consider an entire 500 million years worth of data at once, let's zoom in on just the most recent, say, 60 million years. That's this area right here. So now we're looking at just the most recent 60 million years. And again, we can see there are periods that are hotter, periods that are colder. We've got periods of glaciation, periods where we had thawing, and so on. Now we're getting closer to the current time. Let's zoom in even closer here, the last 5 million years or so, and we can see a little more temporal detail than we could see in those other pictures. Now don't lose track of the sight that we're still talking about vast amounts of time here. The y-axis, the x-axis here is still in millions of years ago. Notice there are a number of different cycles, and so if we now consider temporal scales on the order of hundreds of thousands instead of millions, that's taking this last 500,000 or so and stretching it out a bit to examine what the climate has been like in just the last 500,000 years or so ago. And you can see that there have been regular changes here that are associated with glacial events, and so that is shown as a series of two different graphs here. The blue one at the top here is temperature change as a function of time, and the bottom graph here is ice volume as a period of time, and they're negatively correlated, meaning periods where the glaciers were retreating was when it was warming, and so temperature's going up, ice volume is going down, and vice versa. Here we are right now. I wanted to just point this out because we had discussed earlier the time of the last glacial maximum being about 20,000 years ago or so. You can see this point right here at about 20,000 years ago. This was the most recent glacial maximum period, and we have had less ice volume. We've been warming since. So we'll talk a little bit more about global climate issues later on, but let's go ahead now and turn our attention to biomes. So what are biomes anyway? When ecologists talk about biomes, they mean areas which are described as major life zones, characteristic areas on the planet, and if they're terrestrial biomes, they're usually characterized by vegetation type, and if they're aquatic biomes, by the physical environment, meaning salinity and temperature and so on. So let's start with terrestrial biomes, and to give you a flavor for what is meant by biomes. So actually, before I leave this figure, so there's a couple of different views of different parts of the environment, and so it should be clear to you that different parts of the natural environment, the natural terrestrial environment, look really different from each other. So how can we understand these patterns and understand something about the adaptations of plants and animals in these areas, and where we would actually expect to find these on the globe? That's what the sorts of questions that one is considered about in the scientific study of biomes and ecology. So if we consider where are certain kinds of terrestrial biomes, then we can look at figure 52-9 from your textbook, which is in front of you right now, and this shows overall on the planet's surface what are some of the major terrestrial biomes and where are they located. The exact number of biomes varies a little bit with who the authority is that's generating the biomes. So you can see between 10 and 15 or so. Your book has 14, and they picked 6 for special consideration. They're shown up here at the top. And so the tropical wet forest, subtropical desert, temperate grassland, temperate forest, boreal forest, and Arctic tundra. And your authors chose these because they are particularly they're areas of the planet that are particularly extensive or noteworthy in some way. Now, so here's the other ones over here just to fill in the gaps. Now, one of the first things you might notice is there's a fairly strong latitudinal component. And so here's the equator, so here we are at 0. And so the tropics would be what, up to 23.5 north and down to 23.5 south, right? So here's the tropical area right here. Here's 30 degrees north right here. So given what we were talking about earlier with the effects of global circulation patterns, you would certainly expect to find biomes characterized by arid conditions, dry conditions. So things like deserts, you would expect to see that at about 30 degrees north. So can we find our deserts at 30 degrees north and 30 degrees south? Well, here's our deserts right here, this sort of orangey color, and sure enough, there's not a perfect stripe because of the other effects on local climate, but certainly the vast majority of deserts do tend to line up with 30 degrees north and 30 degrees south as shown here. Now, one of the, you might be wondering, well, what's our biome? You know, if we peer here, it's really hard to see. We're right here, right? There's just a little tiny sliver right there, so if we make this a little greater magnitude, we can see it. Okay, there it is, right? Here we are, right here, right? And so what is that? If we do use our color coding, we can see that this little tiny thin strip, which is our own local biome, is described as Mediterranean forest. Okay? And so that is distinct from all these other biomes here. And this, because this is our own biome, we're going to go ahead and chat about it for a minute or so, because it is our biome, even though it's not singled out for special coverage in your textbook. Before I leave this particular graph, I'd like to show you some of the other places where one can find this same biome, this Mediterranean forest. Not surprisingly from the name, the Mediterranean here, and also there's some areas right here and here. So, another name for Mediterranean forest is chaparral. This is not a figure from your textbook, but it is a picture of what should look like pretty familiar landscape, because this is what our own natural areas in fact look like. Again, here's a picture of the Earth's surface to point out where one tends to get these approximately 30 degrees north and 30 degrees south and so on. So what are some characteristics then of Mediterranean forest? Well, they tend to be, on the order of about 30 degrees north or 30 degrees south, more or less. They tend to be associated with coasts, so they are typically found in coastal regions rather than very far inland. Another characteristic of this biome is that precipitation tends to be extremely seasonal. So for example, with rainy winters, at least when you're not having a big drought, and then also dry summers. That is the overall characteristic pattern. The temperatures do tend to be fairly mild, as you know from your personal experiences of our local climate. And what can we say about the plants? Well, the plants tend to be characterized by a lot of small shrubs as opposed to great big trees. You don't tend to get a lot of very large dense trees in this particular area, so you get a lot of shrubs. You do get small trees, lots of grasses, so on, other kinds of plants, and then animals which consume these kinds of plants. You also do tend to get plants that have various adaptations to drought and also fire, because these are two phenomena that the living organisms have to be able to deal with to live in this particular biome. Okay, in the remaining 2 minutes here, I'm going to go ahead and do a quick dash through the next biome. Tropical forests. Where do we find these? Well, not surprisingly, in the tropics. You would expect to find these what? Between the two tropics, the Tropic of Cancer and the Tropic of Capricorn. So between 23.5 degrees north and 23.5 degrees south, straddling the equator. This is where one finds tropical forest. There's a picture on the right showing what a typical tropical forest looks like. Notice it's completely different from the natural vegetation in our own biome. And in part, this is driven by precipitation, meaning how much rainfall do tropical forests get a lot? And the answer is a lot. This is the graph shown down here at the bottom. The y-axis is average precipitation in centimeters throughout the year. And compared to other biomes, the annual total is extremely high. Tropical forests tend to be very, very wet, get tons of rain. There is, in fact, also very high variation in the rainfall, but not in the temperature. Check out the temperature at the top here. This is a graph of temperature versus month. Look how flat that graph is. It tends to be very hot with very low variability, meaning it's hot pretty much all the time. Okay, we're out of time, so it's time for me to just wish you a very happy weekend, and I'll see you on Monday.